Hi there once again. On this video you're going to learn about exponential functions. Okay, it's this letter E. Alright, there's nothing really complicated about this letter E. It's basically a number. Alright, um, it's this number 2.71828. There's no end to it. There are lots of decimals after that. It's a number like pi. Alright, it's this number here. Okay, so you first have to learn to sketch this graph. Y is equal to ex. All right, now here again there's nothing complicated about this. You already learned what this graph looks like. Okay, you've learned that in core 2, haven't you? In chapter 3 in core 2. You also know how this graph looks like. Y is equal to 3 to the power of x. Okay, so y is equal to 2 to the power of x. Okay, now looks something like this, doesn't it? Why does it look something like that? All right, when x is equal to 0, that's 2 to the power of 0, you have 1. So at x is equal to 0, y is equal to 1. When x is equal to minus 1, that's 2 to the power of minus 1, which is a half. So when x is equal to minus 1, it's a half. Okay, and when x is equal to 2, it's 2 to the power of 2, which is a 4. Okay, if you look at this graph, now let me draw that graph. Okay, so this is drawn in white, this is drawn using green pen. So when y is equal to 3 to the power of x, it looks something like this. Okay, right, it'll be a bit more steeper on this side and steeper still on this side, because when y is equal to x is equal to 1, y is equal to 3. All right, and when x is equal to 2, y is equal to 9. Whereas on the y is equal to 2 to the power of x, when x is equal to 2, y is equal to 4. All right, whereas when x is equal to 2, y is equal to 9 on the y is equal to 3 to the power of x graph. Okay, I told you before that this letter E is nothing but a number. All right, 2.71828. So if I want to draw this, y is equal to e to the power of x, it'll look the same as these two graphs, but it'll go in between these two. All right, let me get that absolutely correct. Whoopsie daisy. Okay, it looks something like that. All right, so let me draw that separate. Okay, y is equal to e to the power of x. Okay, it'll basically look the same shape. Okay, unless you're asked to draw all three graphs or all two of these graphs on the same axis, then you'll have to show which one's above the other. Okay, but if you ask to draw only this, it'll be the same as drawing this or this, same shape. Okay, and this coordinate where x is equal to 0, y is equal to 1, that'll be the same for that as well. Okay, because any number raised to the power of 0 is always 1. Okay, good. All right, now for now, just okay, now I'm sure most of you are curious, why this number, why not a 2, why not a 3, why in maths and in science, why we persist with this value called e. Okay, now after I've explained all the stuff you need to know for the syllabus, I'll do a little bit on why we choose this number. Okay, that's right at the end. Okay, right now I just want to make sure that you pass the exam and get a good mark. Okay, right at the end of this video I'll explain to you why we persist with this number called e. Okay, for now you just want to pass the exam. Okay, good. Okay, so stay with me. All right, now you also know that there is an asymptote on the x-axis. Okay, but if the asymptote is on the x-axis, we can't show it using a dotted line. All right, so if we transform this e to the power of x graph, so if we shift it up, all right, so if you did y e to the power of x plus 1, then you'll be able to see that asymptote. All right, so this point here, when x was equal to 0, y was equal to 1, that point there, It's now going to get shifted by 1, so that's going to be 0 comma 2, plus you're going to be able to see the asymptote on the y is equal to 1 line. So that graph looks like that. Okay, good. So you can do all sorts of transformations to this. So if you did y e x minus 1, what would that look like? Okay, that basically shifts the whole graph to the right by 1. Okay, so that point there where you had 0 1 would be now here at 1 comma 1, because you shift the whole graph by 1. Okay, good. Now you're going to look at a notation called ln. Okay, there's no mystique behind this, there's no magic behind this. Ln is basically equivalent to log to the base of e. All right, now here again, you've learned this before. You know what log to the base of 2 is. Okay, so if I did log to the base of 2, 8 like this, you know what the answer is. That is 3. If I wrote this in indices form, it's 2 to the power of 3 is equal to 8. Okay, if you had log 2 of 2, that will be equal to 1. All right, so log e is basically a number. 2.71 goes on like that. All right, so if I had log e of e, that would be equal to 1. Or instead of saying log e of e, I can say ln. Whenever you say log e, that's basically equal to ln. Okay, and that is equal to, if ln of e is equal to 1. Okay, it's similar to a situation like this. Okay, because that's 2 to the power 1 is equal to 2, so e to the power 1 is equal to e. Okay, all right. You also need to be able to sketch the log base of e graph. Okay, or the ln x graph. Okay, so y is equal to ln x graph. All right, okay, how would this look like? All right, now what this means is that e to the power y is equal to x. Okay, because that's a log base of e, isn't it? So e to the power y is equal to x. Okay, so my x values here are powers. No, sorry, x values here are results of e being raised to the power of y. Okay, all right, good. Now if e is positive, this x value could never be negative. All right, okay, I'm going to replace an e with a 2. Okay, 2 to the power of y is equal to x. Okay, now this x value can never be negative. Okay, if I raise this 2 to any power of y. Okay, so for this graph, y is equal to ln x graph, the domain can never have negative values. All right, because when e is raised to a certain power, it can never have a negative value. All right, so the domain, so when I'm sketching this y is equal to ln x graph, the domain has to be greater than 0. Okay, so there is an asymptote on the axis. Okay, can't quite see that usually, because if the asymptote is on the axis, you can't really show that. Okay, but I've just drawn that with a dotted yellow line. All right, good. When x is equal to 1, y is equal to 0. All right, just think about this. When x is equal to 1, y would have equal to 0, isn't it? Any number raised to the power of 0 is equal to 1. So when I have x is equal to 1 here, y is equal to 0. Okay, okay, if x was equal to something like 0.5, then y would have to equal to some negative power, isn't it? Okay, yeah, I don't know what it is. Maybe it's negative 0.75. I don't know what the precise value is, but it is a good example though. If x has to be 0.5, y has to be equal to minus 0.75. Okay, so therefore it'll be something like this. Okay, now let me replace this with a 2. Okay, then it'll make more sense. Okay, so 2 to the power of something would have to equal to 0.5. It'll have to be y would have to be y minus 1, isn't it? For 2 to the power of minus 1 is equal to 0.5. So it's a similar situation like that. Okay, so it has to be equal to negative power for that result to be a decimal answer below 1. Okay, so when x is 0.5, y would have to be some negative power. Okay, so as this value gets smaller and smaller, the y negative power of y would have to increase in the negative scale. Okay, so these values would increase like this. All right, so there's an asymptote on the x is equal to 0 line. Okay, and the graph looks something like this. Okay, there's no asymptote on the y line there. All right, increases. Okay, but it flattens out. Okay, so there's a coordinate here that is 1 0. Okay, the ln x graph, y is equal to ln x graph, is in fact the inverse graph of y is equal to e to the power of x. So this is y is equal to ln x. So how does the inverse graph relate to its normal graph? Okay, it's a reflection on the y is equal to x line, isn't it? The reflection on the y is equal to x line. So that's the y is equal to e to the power of x graph, and that's the y is equal to ln x graph. Those two graphs are inverse. One is an inverse of the other, so therefore it's a reflection on the y is equal to x line. Good. Now we'll see how we can solve questions like this using natural logarithms. Okay, now you've learned this in code 2. To figure out what this x is as a power of e, you'll have to take logs on both sides. Okay, now in code 2 you've learned how to do this way, by taking log base of 10 both sides. Okay, so you would do log of 10 5, and then log of 10 e x, and then the x comes forward, and that's log base 10 e, and then log base 10 5, and then you divide log base 10 5 by log base 10 e, you get x. Okay, now this method is valid. Okay, but what if I take, instead of log base of 10, I take log base of e both sides? All right, so if I did ln, so log base of e is basically ln, so that's ln 5 is equal to ln e x. So I bring the x forward, I get ln e and ln 5. All right, now this is log base of e. All right, now that is equal to 1, isn't it? Okay, we looked at that right at the start. Okay, I'll show you it here. All right, if that's log base of 2, it's equal to 1, because that's basically 2 to the power of 1, and that's equal to 2. Okay, if you wrote that in indices form. So that same thing applies for the log base of e. Okay, log base of e is ln e, that is equal to 1, because e to the power of 1 is equal to e. So whenever you see an ln and an e next to each other, that is equal to 1. Okay, now lots of students just remember it that way. So they'll just say, oh, if you ln and e, you'll get 1. Okay, that doesn't make any mathematical sense, but it's an easy way to remember it. So whenever you see an ln and e next to each other, that makes a 1. Okay, and that x is what you just get. All right, because that x comes forward, doesn't it? Okay, the power comes forward. So x is equal to actually ln 5. Okay, now this is easier to solve than doing it this way, taking log base of 10. Make sure you take log base of e both sides, and then you can get what x is. Good. Now we'll look at something else. All right, we'll write this in ln form now. Ln x is equal to 8. Okay, to do this, now ln is actually log base of e, isn't it? So log base of ex is equal to 8. If I write this in indices form, that's e to the power of 8 is equal to x. Okay, so this is what actually happens. You write it like this, and then you write it in indices form. Here again, lots of students do this. Okay, you actually got to understand what the process is involved there. Okay, they'll just say I'm going to e an ln. Okay, now that again doesn't make any mathematical sense. All right, but they just say they're going to e an ln. So if you took this as powers of e, okay, so they'll just do this. Okay, and therefore if it's e and ln next to each other, that creates an x. Okay, there is no mathematical procedure there. What has actually happened is this bit here. Well, it's a quick way of remembering it. If you have an e next to an ln, that cancels itself out and you just end up with that x. Okay, so you end up with the same answer, but you actually got to remember what actually happens there. Okay, there is no magic procedure here. All right, this is what happens. All right, but they remember it. Lots of students use this method to remember this quickly. They'll just say they are eing an ln x. Okay, then you just get that x, but this is what actually happens here. All right, so whenever you have an e, you ln it. Okay, all right, to get rid of that's right, whenever you have an e, you ln it, so you get rid of the ln and the e, so you just end up with that power of x. Okay, but this is what actually happens there. All right, you've got to be able to know this. Okay, so that when it's a bit more complicated, you'll find your way easily. All right, and whenever something is given in terms of an ln, you e it. Okay, but this is what actually happens there. Okay, you write it in indices form. Okay, you write it in terms of log. Okay, not just ln, and then you write it in indices form. Okay, but you can just say I'm eing an ln. Okay, and then those two cancel out. All right, good. Okay, now we'll look at a practical application where you use e and ln. All right, now look at this formula. N stands for the number of bacteria, T stands for the number of days. Okay, so this is basically the population of a bacteria culture as the days go by. Okay, so how it increases as the days increase. Okay, so when T becomes larger, you can see that the number of bacteria increases. Okay, because T is the number of days, so on day 1 you'd have 1 over 20 to the power of e to the power of 1 over 20, that times 50 plus 100. Okay, so as T increases, you can see that this value keeps on increasing, and that would be the number of bacteria that you'd have on any given day. Okay, right, so the first question is how many bacteria you have before you start this experiment. Okay, bacteria at start. Okay, so you'll have to make T is equal to 0, so that's 100 plus e to the power 0 divided by 20, so that is equal to 100 plus 50 e to the power of 0. E to the power of 0 is 1, so 1 times 50 is still 50, so the number of bacteria that you had right at the start was 150. Okay, next question is what's the number of bacteria you have when T is equal to 10. Right, so here again I substitute 10 instead of T, so that's 100 plus e to the power of 10 over 20, that is equal to that times 50, isn't it? Okay, that's the next step, and afterwards I've got to times that by 50 and add 100 to it, that is equal to 182.4 bacteria. All right, the next question is when would the bacterial population be equal to 10,000? Okay, on which day would the population reach this value? Okay, so here again, now in this instance I know the value of n, but I've got to figure out what my T would be for that. All right, so that's T is the unknown. I've got to make T the subject. All right, so watch this closely how I do this. So 10,000 minus 100, that is 9900 is equal to 50 e to the power of t by 20. I divide both sides by 50. That gives me 990 by 5 is equal to e t by 20. 990 divided by 5 is 198 is equal to e to the power of t by 20. Okay, now here is the place where I got to ln this e. Okay, basically what I'm doing is this. I'm taking logs, natural logs on both sides, and that becomes ln 98. That stays the same, but that t by 20 comes forward because that's a power, and then ln e I'm left with. Ln e is 1, so t by 20 is equal to ln 198. Now all of this could be done by you just saying I'm just going to ln this e. So ln 198. So if you did an ln of an e, you just get what the power. You just get the power. All right. So that's the same point we are at here. Okay. You don't need to show this all the time. It's just understood what has happened here. Okay. So I've got to solve this now. So that's 20 times ln 198 is equal to t. So t is equal to 105.760. So on this day, the population has reached 10,000. Okay, and I've solved it by doing this. Okay, good. Now right at the beginning of the lesson, I told you that E is used a lot in practical applications in maths and in science. Now you noticed a situation where I've used E to solve a practical problem. Okay, so they've modeled the growth of a bacteria using this formula. All right. Okay, so that means that the population of the bacteria increases exponentially. So if I were to sketch this graph would look something like this. Okay, the population increases exponentially, and that point is 0, 150, because right at the start you had 150 bacteria, and the population increases exponentially. All right. Okay, now why we persist with E is because when you go to find the rate of change of something, okay, now let me stick with this same formula, 100 plus 50 e t by 20. Okay, you learn this later on in core 3, is that when you differentiate something that is raised to the power of e, okay, so when you if your equation is just this, y is equal to e to the power of x, when you differentiate that, you'll still get the same function back. All right, so the rate of change of x is equal to the y coordinate of x. Okay, now let me put that in context. Okay, so let's say a certain bacterial population. Okay, now let me make this equation simpler. Okay, let's say the rate at which the bacteria grows is this. Okay, none of these complicated bits there. All right, so this is this is not the rate, this is the population of the bacteria on any given date. Okay, so on day number 2 you substitute 2 and you'll figure out how many bacteria there are. Okay, but if I want to find the rate of increase of the population of a bacteria, okay, or the rate of change, okay, so that will be given in terms of per day, so many bacteria per day. So that is basically your differentiating there, so dn over dt. When you differentiate, I still get et, because that's what you get when you differentiate e to the power of x. Okay, so when that is e to the power of t, even when you differentiate that, the rate is going to be actually equal to the number of bacteria there are. Okay, sounds silly. Okay, so let's say on day number 2 what's the rate of increase of bacteria and the number of bacteria. Okay, the number of bacteria on day number 2 would be e to the power of 2. I use this formula. The rate would be also equal to e to the power of 2. So this is bacteria, and whereas this is bacteria per day. Okay, so that's something very unique with this number e. All right, so if I were to sketch that, on any point, on any given point on this graph, the gradient, okay, the gradient of this line is equal to the y coordinate. Okay, so let's say the gradient at x is equal to 2, that is equal to 7.39, and the y coordinate is also equal to 7.39. so there will be 7.39 bacteria on that day, plus the rate of increase of bacteria is also 7.39. okay, so that's why this value of e comes in handy. All right, now let's take another example. All right, now let's say you all know about compound interest, don't you? Okay, so let's say your investment after a certain year, okay, if the rate is 5%, okay, the rate is 5%, and the amount you invested, that could be anything. Okay, let's say you invested 1,000 pounds. Okay, so you want to figure out after 5 years what your investment is. You use this formula. Okay, this is for compound interest. All right, okay, so let's see what your investment after 5 years is. N is equal to 5 years. So let's see what my investment is after 5 years. Okay, this is my investment. Okay, right, so I want to know what's the rate of increase of my investment. Okay, the rate of increase of my investment. So every year, what is the rate at which my investment is increasing? Okay, so the rate increases, doesn't it, as you as the years go by, because it's not a linear increase, it's an exponential increase, isn't it? Your investment increases. Okay, so to find the rate of increase of your investment, you'll have to differentiate this. Okay, now differentiating something like this is a bit tedious. Okay, so if you can bring in an e into this, that makes this whole process simpler. All right, so I'll show you how to bring an e into this. I'm just going to take out this 1.05 n bit, okay, and try and bring an e into that. All right, so let's say I'll make this equal to e to the power of x. So then if I did ln both sides, I get x is equal to ln 1.05, and that n comes forward. All right, so therefore x is equal to ln 1.05. okay, so if I had e to the power of n and ln 1.05, that would be equal to 1.05 to the power of n. Okay, so this one here, I've now brought it in terms of an e. I've changed this in terms of an e. Okay, now that makes differentiating very easy. Okay, oopsie daisy. Okay, now let me rewrite that formula in terms of what I have found here. So that's e n ln 1.05. all right, I. Okay, now I can figure out what ln 1.05 is, which is okay, ln 1.05 is 0.0488. Now this formula is exactly the same as this. Okay, If you want to test it, now let's put 5 for n and our investment being 1,000. Okay, 1,000 pounds. Okay, let's substitute these two same values in and see whether we're getting the same answer. Okay, so that's 1,000 and e 0.0488 times 5. Let's see what we get. Okay, so the answer is in fact exactly the same. All right, the answer is exactly the same. Okay, even though I've changed the formula so that it has an e in it. All right, so the formula is this now: a times e to the power of n 0.0488. Okay, now I said to you I want to find the rate of change of my investment, okay, on year 5. Okay, so that is basically di over dn. Okay, investment per year. Okay, all right, so that's my rate. So if I differentiate that, okay, here again the differential of this is, you learn this in code 3 chapter 9. I just have to put this value here as well. Okay, so it makes it very easy for me to differentiate, okay, and find the rate. Okay, whereas something like this is a bit more difficult to differentiate. Okay, so that's why I want to change that formula so that it has an e in it. Okay, so in many applications where it's an exponential increase, irrespective of how the actual formula looks like to to what number you're raising it, okay, here like a number like this, you always try and bring it back to an e so that the differentiation process becomes simpler. All right, so that's what I'm trying to show you here. Okay, that's why you treat this e specially, because it has this amazing property where that when you differentiate e to the power of x, you still get e to the power of x. And if you differentiate something like e to the power of 2x, you'll get 2e to the power of 2x. Okay, which makes it very easy to find the rate of change of something. Okay, so if you didn't understand what I did in the last 5 or 6 minutes, no problem at all. You won't be questioned too heavily on what I've just done, but it just helps you understand why we persist with this number called e.